There's an interesting thing I'd like to show you here. And, it's something that I didn't realize. Okay. So let's take the square root of 4. Now, as we were talking before, the square root of 4 is really the second root of 4. And so what we're looking for are two numbers or one number such that when we multiply it by itself, you get 4. Okay. And so the most common answer is that the square root of 4 is 2. Okay. So x would equal 2. And therefore 2 times 2 equals 4. Now, some people know, and then now you definitely know because we talked about it, that when you express the square root, and unless you're given some other instruction to ignore it, you have to list plus or minus 2, because negative 2 times negative 2 also equals positive 4. But here's the thing I'd like to focus on, is that the root, or the index rather, of this root is 2. And so what that means is there must be two solutions, okay, or roots. There must be two roots. Now, this is super cool, okay? So for this example, one of our roots was 2. And the other one was negative 2. Now, here's what I'd like to do. I want to write this out in complex form. So that's 2 plus 0i, and then negative 2 plus 0i. Now, for a number to exist only on the real axis, let's take a look at a complex plane. Okay, here's a complex plane. In order for a number to only exist on this horizontal axis, it's the imaginary component of the complex number would have to be 0. Okay. Here's your real axis. And so let's say 2 is plotted. Probably should have put, since I've got the graph paper, probably should have done this a little bit of a different way, where I center it like that. So we could call this 1, 2, negative 1, negative 2. So here's your negative 2 solution or root, and here's your positive 2 root. Here's the cool thing I want you to think about. How many roots are there? There are 2 roots, all right? One of them is plotted right here, and one of them is plotted right here. What is the angle of rotation between the 2 roots? Okay, you start at 0, and you're going to have to spin 180 degrees to get over to that second root. So if we were to superimpose a circle on this thing, like this, then you would have to rotate 180 degrees. Okay, so here's how I'm looking at that. I'm looking at 360, which is the total number of degrees around the circle, divided by whatever this number is. Okay, divided by whatever this number is, and this is the degree of separation between each of the solutions. So in this case, it's 180 degrees. Well, that's easy. If you find the first solution, you just go 180 degrees opposite that solution, you'll find the second solution. In fact, if I were to draw a better circle, one that just went from one of these solutions to the other, and I'll adjust this so that this circle right at the center and its perimeter is touching these solutions. We'll get it. Kind of like that, okay? Then the angular travel from here to here is 180 degrees. Very interesting. Now, what I want to do now is look at this question, which is the cubed root of 27. I want to look at the cubed root of 27. And so here's my claim. My claim is, without even hesitating a nanosecond, I can tell you there are going to be 3 roots. Now, I bet you can only name one of them. You know, if you're just thinking about it, I need some number, x, that when I multiply it by itself 3 times, I get 27. Well, if you're clever, you probably think 3. 3 times 3 is 9. 9 times 3 is 27. Yeah, that checks out. That's one of the solutions. But what about the other 2? Can you think of another set of 3 numbers that when you multiply them, or another set of numbers that when you multiply it by itself 3 times, it's going to be 27? Because according to this rule that I was reading about, there have to be 3 roots. Well, here's the deal. This is the real root, 3. Written in complex form, that's 3 plus 0i. Here's the deal. There have to be 2 other roots that include some complex I, okay? And so how are we going to figure that out? Well, I'm glad you asked. So, first of all, we can identify the degree of these roots by taking 360 and dividing by 3. 360 divided by 3 is 120 degrees. And so what that means, ladies and gentlemen, is that each root is offset by a rotation of 120 degrees from the previous root. Let's get a circle going on so we can see this in action. Okay. And then let's get a graph drawn in between those 2 points. Like so. I don't know. There. All right. And good. Awesome. Okay, so our first point here was at 1, 2, 3. There it is, 3. Now, we need to rotate 120 degrees. Here's 90 degrees. Here's 180 degrees. Okay, so we're going to have to find 120 degrees. Now, the way this little tool that I've got here works is I could back off a certain number of degrees, okay, from 180. So if I think if I rotate this thing 60 degrees up like this, I will be at 120 degrees rotated counterclockwise from 3. So if I put this right here and I draw like a little scroll line here, somewhere along that little line that I drew is going to be our solution. This is so cool. I just can't. Okay, so now where's the other solution? So now from this point, we need to rotate 120 degrees. So if we were at 120, we need to be at 240. All right, well, 240 is close to 270. That's down here. This is 270. So I think if I start here at 90 degrees, you kind of think if I go from 270 to 240, that's 30 degrees. So if I start rotating down like this, if I take 30 off of 90, I'll rotate until I'm at 60. And then I should be at 240 degrees of rotations from that 3. All right, so here comes the pencil again. This is really, I mean, this is mind-blowing that this is real. Okay, that's not a very good line. We need it for, I think for this purpose, it's got to be perfect. Okay. Right there, maybe. Did that work? Good. I'll take that. Okay, so now where are these going to be located? Well, here's what I think. I think that if we take a circle like this and we start putting this circle to where its center is at the center of the circle and it's passing through 3, I'm claiming that the other two roots are right here and right here. So one of the roots is going to be rotated 120 degrees, and the other root is going to be rotated 240 degrees, like this. But I think those roots are going to be on the same level or the same ring as the first root, that 3. So I got to figure out what these coordinates are. Well, you know, the thing to do is to look at it kind of visually. So over here I've got 1, 2. So it's between 1 and 2. It's like, looks like 1.75, and then up 1 to about 1.75. So, well, that's just my guess. My guess is that one of the roots is going to be 1.75 plus, or negative 1.75 plus 1.75i. Okay, just a guess. I mean, we'll get it precise later. And then the other one's just opposite of that. So that would be negative 1.75 minus 1.75i. Okay, so how would we figure out exactly the correct answer? Okay, well, first we need to identify, or we need to make a note that the magnitude of these vectors is 3. Okay, the magnitude of the vectors is 3. You've got 3, 3, and 3. So we need pi notation now. So this is 2 pi, this is pi over 2, this is pi, and this is 3 pi over 2. Okay, so if I'm on 0, in other words, if I'm over here with this 3, I can write this in exponential form as 3e to the 2 pi I. And guys, this just equals 3. If you don't believe me, we can plug it in and check. If I hit 3 and then I put in the transcendental number e, and then I raise that to 2 pi, and then I put in I got to make sure I'm in radian mode. I wasn't. Okay. And you hit enter, it's just going to be 3. So 3e raised to the power of 2 pi I is just 3. Now, what I claim is, if we can figure out the radian measures for 120 degrees and 240 degrees, I think I can write, anyway, let's go through it. So 120 degrees. So you got 120 times pi over 180. Cancel the 12 and the 18 and do a 6 factor. Okay, so 12 divided by 2 is, or 12 divided by 6 is 2. 18 divided by 6 is 3. So I got 2 pi over 3 is 120 degrees. And then for 240, so I take the 240 times pi over 180. Can cancel the zeros out. And then for 24, we'll use, for 24, I guess we'll use 6. So 24 divided by 6 is 4. 18 divided by 6 is 3. So my radian measure is 4 pi over 3. So here's what I claim, that for all of these are the 3 solutions now. One is 3e 2 pi I, which is just this one. Okay. The second one is going to be 3e 2 pi over 3i. And the third one's going to be 3e 4 pi over 3I. Now these have numbers, okay? They have magnitudes, but those magnitudes don't help us actually plot these answers. So let me show you how to use Euler's formula to take these things and turn them into polar coordinates, okay? So what you do is you take the magnitude of the vector, called the modulus, and you put it here outside. And then you do open parentheses. And then it's cosine of this radian measure without the I, just so cosine of 2 pi. Here we've got cosine of 2 pi over 3. And here it's cosine of 4 pi over 3. Of course, all this really means is cosine of 0 degrees, cosine of 120 degrees, and cosine of 240 degrees. Anyway, then we do plus the sine of, okay, we're building the equations all at once, of 2 pi I, of 2 pi over 3 I, of 4 pi over 3 I, okay? And then you close those parentheses off. Now remember, this is still, if you were wanting to use degrees instead of radians, it's 0 degrees, 120 degrees, and 240 degrees, okay? But we're going to use the radians. Well, maybe we'll write it both ways. So anyway, then we can distribute the 3, to each term, and we do that for all 3 of them. And so I guess we can write out these are the exponential notation here. The exponential notation here, and then we've got the complex here. So my first solution, which is going to be this right here, will equal 3 cosine 2 pi plus 3 sine 2 pi I. Okay, again, it's 0 degrees, 0 degrees. Guys, the cosine of 0 degrees, or the cosine of 2 pi, is 1, okay? So this is actually equal to 3 times 1. Okay, the cosine of 0 degrees is 1, plus 3 times the sine of 2 pi, or 0 degrees, I. Well, it's the sine of 2 pi, or the sine of 0 degrees, is 0, because the height of a triangle at the 2 pi marker here at 0 degrees, the height of the triangle is 0. There is no triangle. And so that's 0. And then I times 0 is 0. So you see that first solution, that's why it's 3, because everything's 0. So it's, if you wanted to put this, 3 times 1 is 3, plus 0 just equals 3. So that first solution, even though it's got this cosine and the sine, when you figure it all out, it's just a whole number. And so that's why that's a whole number. Okay, that's this solution here. And so now we're going to write out the next one. Okay, so this was solution 1, and we'll call this solution 1, and here it is, 3. Okay. Now we'll do the second one. The second one said that we had 3, and we'll distribute it out. 3 cosine, let me zoom back in. 3 cosine of 2 pi over 3 which is 120 degrees. If you're keeping track, I guess I better keep the color scheme going. This is 120 degrees. So the location we're looking for right now is this one, okay? That's the one that's rotated 120 degrees. All right, plus 3 sine of 2 pi over 3, which is just 120 degrees, ladies and gentlemen. All right. And this one will have a non-zero I value because you see it exists in the complex plane somewhere between perfect imaginary and perfect real. So we are definitely going to get a real and imaginary component here. So here we go. Let's figure it out. So we could leave it in this form, by the way, because this is the exact form, but that's not much fun. Hey, remember that my guess was that it was negative 1.75 plus 1.75i. I think we need to make sure that we remember that this is negative when we write it in rectangular form. Anyway, so let's approximate the cosine of 2 pi over 3. Aha, negative 0.5. Good. Okay, so it put the negative for us. And then multiply that by 3. Negative 1.5. Okay. So this whole thing evaluates out to negative 1.5. Here come your rectangular coordinates. So I thought it was 1.75. It was pretty close. Plus, now we'll do sine of 3 times the sine of 2 pi over 3. Here's what the sine of 2 pi over 3 is. We would expect it to be positive, right? 2 pi divided by 3. 0.8660. Okay, well, let's multiply that by 3. 2.5981. Okay, so we'll go over here and do 2.5981. I think we do better on that 8. 81 I. All right, so I was a little off. In fact, I don't even know if I need to check and see if this is valid. So you can think of this as the x value and this is the y value. And so you can also think of this as the base of a triangle and this as the height of the triangle. And so if you were trying to find the magnitude of a vector and you had a triangle and you knew that its base was negative 1.5, well, we just take the absolute value, and the height was 2.5981, and you wanted to know c would just equal the square root of 2.5981 squared plus 1.5 squared. So we'll go ahead and put square root of that squared plus that squared. It won't matter. Well, actually it could matter. So I want to put this in parentheses and we don't need the negative. It doesn't make any difference. And then we'll put the squared here. So that's 3. Okay, good. So this works. So this means the magnitude of the vector was correct. I was just checking. I was somewhat concerned that we wouldn't end up with 3. All right, so c equals 3. That's good. Okay, that means that this still works. So my hypothesis there is working out really great, that the magnitude here, the modulus, is 3. The argument is 120 degrees. So in rectangular coordinates, here's your rectangular coordinates. Here are your polar coordinates, and your exponential expression was right here. Very cool. Okay, so that's the second solution. You can look at it like that. And finally, the third solution. Okay, well, we'll see. We'll see how much of this curly Q nonsense we need. So we got 3, and then it's cosine 240. That's just 4 pi over 3. All right, so I got 3 cosine of 4 pi over 3. I just can't. It's 4 pi over 3 plus 3 sine of 4 pi over 3 I. Now, this is 240 degrees of rotation counterclockwise. All right, so let's figure it out, guys. Let's do 3 times cosine 4 pi over 3. Negative 1.5. Okay, it's exactly the same. Remember, it would be, because these are on the same, they would be on the same x value. Good. Okay, so that was negative 1.5, just what we thought. Okay, plus, and then we're going to expect this to be negative, right? We expect the sine of 4 pi over 3 to be negative. So now we'll do sine of 4 pi over 3. It better be negative. Negative 0.866. So just the antithesis there, opposite, times 3. Okay, so it's negative 2.5981. This is great. So this is negative 2.5981 I. We already figured that the absolute magnitude there is 3. So need a new color. Purple. This is also 3. Okay. This is 3. So in other words, the hypotenuse of the triangle, the radius of the circle, the magnitude of the vector, and the modulus of the complex coordinate is 3. For all, look at this. So here's our first one. It's also 3. So there's kind of the thing that I wanted to show you here. So you've got all 3 of them, and they're rotated almost like 3-phase. I mean, this is phasor algebra, and so I'm sure there's a connection there. That is super cool. Guys, I don't know if you understand how cool this is. There are 3 solutions or 3 roots to the square root or the cubed root of 27, and they are offset from one another by exactly 120 degrees when you graph them, and here they are. I mean, look at this. So I want to write this all out just so I don't actually forget this. I've got 3 roots. Okay, so we'll say that the cubed root of 27 has 3 roots. And we're going to write those roots. We'll do root 1, we'll do root 2, and we'll do root 3. And we're going to write it out in exponential, polar, and rectangular. Okay, let me move this one over a little bit. So we're making our table here. I'm just totally fascinated by this. I hope it's interesting to you as well. I'm going to be honest, I had no idea. I mean, I assumed, I guess I'd thought about it before that there had to be 3 roots, but I had no clue what the other 2 would be because I couldn't think of any numbers that would do that. Okay. So here's our exponential, and I guess we better test these. So we have our exponential. The first one was 3e raised to the power of 2 pi I. And we know that in the polar form, that was, oh, this polar form is going to be a little cramped. This is going to be 3 cosine 2 pi plus 3 sine 2 pi I. A little cramped in there on that one. In fact, let me zoom in here and write it at an angle. 3 cosine 2 pi plus 3 sine 2 pi I. And then the rectangular version of that was just 3, okay? Because it had an imaginary component of 0. I guess we'll write it like that. All right, so the second one was, I think it was 3e to the 2 pi over 3i. I think that's what it was, right? Yeah. Okay, so this one, remember, was for 0 degrees, and this was 120 degrees, and this was 240 degrees. Okay, so our polar coordinates were 3 cosine 2 pi over 3 plus 3 sine 2 pi over 3i. All right. And so the final form would be the rectangular form. And so the best I can do there is to give an approximation. And here was negative 1.5 minus 2.5981i. Okay. Now on to the final one. And that was 3e to the 4 pi over 3i, which was 3 cosine 4 pi over 3 plus 3 sine 4 pi over 3i. And then that was, hold on, this one was positive. And so this one over here was negative 1.5 minus 2.5981i. This one was positive. Okay. So here are your 3 solutions. The thing I'd like to check is I'd like to make sure that these other 2, when cubed, actually result in the answer being 27. Okay. So here, let's do this. Let's go build this thing. There we go. Negative 1.5 and then plus 2.5981. There. I. Okay. Now we're going to square or cube the answer. Okay. If this equals 27, my mind is going to be totally blown. Wow. That's so cool. Look, if you say, well, that doesn't equal 27. If I set the float to 0, it will. Check this out. Now I got to go do this again. Negative 2 plus 3i. Okay. Let's see. Maybe now I've ruined the float. Okay, so let's see. 27. Okay. So let me put my float back. Amazing, amazing, amazing. That is so cool. Because it includes a negative number. You just would not think. You just would not think. I'm completely blown away. I'm just blown away. Okay, so then we almost don't need to check the last one, but let's check it. Negative 1.5 minus 2.5981i. And then we want to cube that. It equals 27. That is just amazing. That's just amazing. So I hope this was interesting. So the cubed root of 27 consists of one real number, which is 3, and then 2 complex numbers. And this is the picture that just blows my mind. So these are all the roots of this cubed root of 27. Here are all the roots plotted. 120 degrees rotated out of each other's way. That is just unbelievable. That is so cool. Well, I do hope that if you watch this whole video, you learned at least one thing that you didn't know before you started the video. So thanks for watching.